In this video, we'll be talking about something called Maxwell's equations. Now, Maxwell's equations give the general rules for how do you find the electric and magnetic fields given the things that create electric and magnetic fields, like charge and current. Now, they're also fairly popular. By the way, at the level which physics stuff tends to be popular, not as popular as say equals mc squared, which is commonly known. Popular, you will see people walking around with T-shirts with Maxwell's equations on them, like is this. Note that usually when they write these Maxwell's equations, they also have some sort of connection with light, and we're going to try to understand why that is later on. And I want to talk to you what's sort of the importance of this, because remember these equations find the electric and magnetic fields. If you have that, the electric and magnetic fields, and you have the force equations, then you can find all the electric and magnetic forces, which essentially tells you all of the electric and magnetic interactions that you have. So it'll explain every single thing that is caused by electric and magnetic forces. And that's basically every single force that you've ever seen, other than gravity. Everything you've ever smelt, heard, felt, touched, tasted is due at some level to an electric or magnetic force. The forces that bind together atoms are electric and magnetic. The forces that then bind together two different, so this is like internally in an atom, between two different atoms that are related to bonding, are electric and magnetic. Um, Basically, every single force, the fact that your hand doesn't fall through a table when you lean on it is because there is a electric repulsion between the electrons in your hands and the electrons in the table. It's secretly behind everything. So in some level, these four equations sort of have buried in them almost the explanation to everything you've ever seen or felt or dealt with. But so it's sort of amazing that you can capture all of that information in four relatively simple equations. Now we won't have time to be able to unpack that all. I mean, at some level, to understand how Maxwell's equations would help, for example, understand something, explain something in chemistry would require probably more like a semester or a year worth of description. But we'll try to understand roughly what these things are saying, sort of the principles they embody, and then mostly focus on how they connect to light. Now, not only are popular, as this is my sort of joke slide here, they may be too popular. I have seen people who actually, well, not personally, but there are people who tattoo them on their arms, and maybe not always the best idea. But you'll see, people will get extremely enthusiastic about this. Essentially, because when they find out that these equations are behind sort of everything and they didn't know they existed, they get really excited, which I think is pretty awesome. But but it is also um, sometimes a little bit too far in their enthusiasm. So here are Maxwell's equations. There are four equations. We have this is the upper left one, left, upper right, 1, 2, 3, 4. There's four equations here. Now, if you look in this line, what I expect you to see is that this is scary gibberish. All of this is done in vector calculus. So these are all vector derivatives. If you've not taken usually what is a third semester of calculus, you've probably never seen any of these symbols, these up, down, upside down triangle symbols. And also the physics on this level is usually a notation you haven't seen to sort of de-scare it a little bit. Rho here is just the charge density, so this is the charge divided by the volume. J is basically the current. It's again a density, so it's a current divided by an area, but it's basically that. Here's the electric and magnetic field. But long story short, I'm going to try to take this scary gibberish and into less scary, or non-scary, non-gibberish. So I'm just going to say here's the equation, and I'm not going to show you the math, but I'm going to say here's the basic idea behind the equation. Now, when you see this upside down triangle, which is called, with a little dot beside, and a letter where they both have arrows on the top, that is referring to something that's called a divergence. And really, what this is saying is that the amount of electric field, and I know it's electric field because it's listed right there that this is electric field, coming out of some spot is proportional to what's on the right hand side, how much charge there is. So this just says the amount of electric field coming out of a spot is related to how much charge is at that spot. If there's no charge at that spot, electric fields can't come out from that spot or go into that spot. If there was negative charge, it would go into that spot, which is essentially what we learned on the first day with electric fields. We said, oh, okay, electric field lines start on positive and they end on negative. Okay, so if I have a positive charge here, then it'll come out, electric field lines will come out of there. If it's a negative, it'll go into there. If there's no charge, then they neither start nor end there, they just flow through there. That's effectively what this is. And this is actually just Gauss's law. This is Gauss's law that we've already learned, just in different language. And if you remember, we talked about with Gauss's law, flux through a surface relating the charge. That's mathematically equivalent formulation to this version right here. And we've showed already that we can get the equations that we already had before for the electric field of a point charge. For example, you can also get the electric field of a large plate using Gauss's law. So this is very, very different notation, but the idea is straightforward. The amount of electric field starting and ending in a location is just proportional to the charge there, and that you can do the whole flux discussion to find the formulas for some of the electric fields that we've already done. The second equation is basically the same thing but for magnetism. So I'll call it Gauss's law for magnetism. It's often called that. And it says the amount of magnetic field coming out from some spot is always zero because there is no magnetic charge. There is no little chunks of north or chunks of south, like there's chunks, little bits of positive and negative. For example, an electron is a little chunk of negative and a proton is a little chunk of positive. There's no such thing for magnetism, so therefore magnetic field lines can't start or end. And that's all this is saying. It's the magnetic field lines never start and they never end because there's no magnetic charge.